All right, it was great to meet everyone today. It was good to see you in class. I'm looking forward to the semester together. Today we talked about bounded and eventually bounded sequences. And so in this video, what I'm going to do is I'm going to go back through some of those definitions, maybe try to clarify them a little bit, and then move forward towards tomorrow's conversation, which is convergent sequences, and kind of set up tomorrow's task. Okay, so let's start with bounded, what we mean to say we had a bounded sequence. And we talked about this a lot, and you guys did a great job. And what we really need to think about is when we're bounded, what's the rest of our definition? And what we really might have is something like bounded above by 10, for example. And you all did a pretty good job of saying how we should think about that. And what that means is that we've got 10 here, and then our sequence values all stay below that value of 10. And so if we had our definition might look something like our sequence is bounded above by 10 if for all n in the natural numbers, a sub n is less than 10. And we had a conversation about whether to use less than or equal to, and we kind of voted on less than. It doesn't really matter in the big scheme of things. The two definitions kind of end up with the same results, no matter which way you want to do it. There are just some subtle differences into how you have to treat different proofs and things like that. If you're curious, our textbook and most of the textbooks will address this with a less than or equal to. But let's use less than because that's what we kind of all decided. Okay, well, let's move and ask the second question, though. The second question, which is what I kind of want to talk about in this video, is what happens if we kind of restrict our definition and say instead that our sequence AN is just bounded above. So what if we say AN is bounded above, but we don't say what it's bounded above by? Well, then what we're really saying is that you have maybe some sequence that looks like that versus some other sequence where maybe we have a pattern of numbers that continue to increase in value. And we might say this first one is an example of one that's bounded above, and the second one isn't. But what's different is if we just say bounded above and we don't give you the specific number that it's bounded above by, then that means that you are tasked with finding that number. So all we mean is that it's bounded above if it's possible to find a number. So notice this first one isn't bounded above by everything. It's definitely not bounded above, for example, by that number right here. That's definitely not bounded above by that, or it's not bounded above by that number here. But it is bounded above by something. And so if it's bounded above by anything, then we say that it is bounded above. And let's just call that point, let's use the letter M just for a good, nice number here. So we'll say AN is bounded above if, so we'll say AN is bounded above if there exists some real number M such that for all n greater than M, or for all natural numbers n, A of n is less than that M value. So the difference is if we're going to do a proof, and the proof just says show that it's bounded above, you have to first go figure out what is the M value that you're going to use, what is this number, and then do your proof with that number. So finding the M value is part of the problem now when we get into these types of situations. Finally, let's kind of move to the last question, which I think is maybe the most interesting and the one we talked about just briefly in class, and that is, what if we just use the word bounded and don't throw any other words on it? So what if I just say a question that looks like this, AN is bounded? Well, what I mean by that is that AN is bounded. What we really mean is bounded if it is both bounded above and bounded below. So if we have a sequence that's bounded, then that means we have both sides attached to it. So if I'm thinking of a picture here, I might think of one picture that looks like this, where I have some dots on here And this would be a nice example of a bounded sequence because I can both bound it above and bound it below versus some other sequence where I might draw it like this, and maybe I have, maybe it comes up here, but maybe as we come down to this side, we keep going forever. And so this sequence would be bounded above, but it is definitely not bounded below. And so since it's not bounded below, the second sequence is not an example of a bounded sequence. So for it to be bounded, you need both an above and a below bound. Okay, so as we think about this, then what you recognize is that a proving something is bounded, really just comes down to making two proofs. A proof that's bounded above, and then a second proof that shows it's bounded below. And then once you put those two proofs together, you have your entire problem. But there's also a second way of thinking about our problem. So notice what we might do is we might do our first proof and show that it's bounded above. And so we have to find this top number. Maybe we'll call that M1. And then this bottom number that's below. And maybe that number will be M2. But notice there's something else we could have done. We could have taken whichever one of these numbers was further from the origin and just used it and negative that number as well. So what we could have done is used, instead of M1 and M2, we could have used just M here. And then I'm going to delete this entire line, and instead of using that line, let's come down and let's just take that distance and go down here and put negative M down here on the bottom. And so we'll have positive M on the top and negative M on the bottom. And you could always make a positive and negative, and you just have to choose whichever one is further from the origin, and then make it your positive and negative values. And this should always work. But what you see from this statement is that we see that all of our AN values must simultaneously be less than M and also greater than negative M. Well, this is great because this, if you go back and remember some things about inequalities and absolute values, this is exactly what it means to say the absolute value of AN is less than M. And so this is one of our homework problems tonight that I'll ask you to kind of think about. I'll ask you to flesh out the details and show that having these two qualities, being bounded above and below, is the same as having this one property, and that's the property of the absolute value being bounded. So it kind of gives us a second definition that we could use as well. So let's come and let's write down that second definition and see if we like it. So this could be our first definition, and a second possible definition would be that AN is bounded if, and now let's think. So what was our definition? We're saying if AN, the absolute value, is bounded below. I needed my little curly brackets here. So AN is bounded if the absolute value is bounded below. But let's remember what bounded below means. It just means for all in, hold on, it means that there exists a capital M such that for all natural numbers in, AN is less than that capital M. The absolute value of AN is less than capital M. So you could think of bounded as two problems, a bounded above problem and a bounded below problem, or you can think of it as one problem and an absolute value problem. And it turns out that the second definition is really useful in a lot of places in mathematics. So don't just completely disregard it. And it's going to be really useful for us, and it's even going to be useful for us in the next few class periods as we're kind of trying to make some of these more complicated definitions. Okay, but again, that's one of your homework problems, is to kind of work through the details, the proving that those two definitions are in fact the same definition. Okay, now let's move on and talk about eventually bounded, and you all did a really good job of eventually bounded, and we'll say eventually bounded above by 10, and we'll see what do we mean by this. And I think you all did a really good job of drawing your picture, and we had 10 here. And you all noticed that your sequence could drop below, but then at some point it come above, and then maybe come below again. And then it's eventually bounded if at some point it stays below from then on. And I like the definition that we created in class today, which said it's eventually bounded above by 10 if there exists some natural number n such that for all m greater than n, am is less than 10. And so this is, like I said, this is a good definition. I like this. One of the important details is thinking about what these different pieces mean in relationship to the graph. And this there exists an n part. Well, that n is kind of this spot here, where once we get past that point, every spot on the graph is now less than our 10 value. So kind of think of this as like a starting value, right? So this little n is telling us where to start, and then once you start at that point, every point beyond that starting value gives us the less than 10 inequality that we wanted before. And so this is a really nice way of thinking about eventually bounded. But notice what happens before that n doesn't really matter. So those points don't matter so much. Okay, let me make one quick point, and that is I want to make one slight, just ever so slight change to this definition. And it comes from the fact that we are saying a sequence an is eventually bounded. And there's just a little bit of confusion in the fact that we have an n right here in our an, and then we have another n right here for this natural number. And they're not exactly the same n. So this first an is meant to be an index, and it could be filled with any natural number. And so it runs from 1 all the way up to infinity. Versus this this definition that we had is just an individual n number. So it's one starting spot. So we're talking about one number versus any of them in the sequence. So what I'm going to do, I'm just going to make a slight change. And my slight change is switching this in for a different number. And the letter I'm going to choose is one that's fairly traditional in the world of mathematics. I'm going to use a capital N. And so we'll say if capital N is a natural number such that whenever m is greater than capital N, a of m is less than 10. And that makes this picture now a capital N right here at that starting point. Don't feel like you have to do this. However, I think it does clean up the language a little bit if we switch that letter from a little n to a big N. I think it kind of makes it a little bit more clear what we're talking about when we do these problems. So if you see this before you finish your homework, feel free to kind of switch our notation as we go through. One problem that you're going to be asked is show that if it's eventually bounded above by 10, then it's bounded. Now, it doesn't mean it's bounded by 10. It means it's bounded by something. And let's look at this picture real quick and just see, why does that have to be the case? Well, what you'll notice, if it's eventually bounded above, then that means we have this point right here, where every point here is lower than 10. But there are a handful of points that could potentially be greater than 10. But how many points are over here on this left-hand side? And the answer is only a finite number of them. So if n is, say, 10, then there are only 10 points over here on the left. If n is 100, there are 100 points. But the important thing is if you have a finite number of points, you can pick out whichever the largest number is. So what we can do is we can make the bound just larger than whatever, say, the biggest one of those values is. And so that's what we can use for our bound to show that our graph is bounded. Bounded by whatever that m value is that might potentially be a little bit bigger than the 10 that it's eventually bounded by. So let me just say that point one more time just for clarification, and that is that when we think about sets, if a set has only a finite number of things, if you have a bucket with 10 numbers in it, then one of those numbers has to be the largest. There could be several numbers tied, but there has to be a largest number in the set. And there also has to be a smallest number in the set. And it doesn't matter how big the bucket is. The bucket has 1 billion items in it. like there's, 7 billion people on Earth, one of them is the tallest. One of them is the oldest. So there exists these most extreme values. If, however, you were to somehow have an infinite number of items in your bucket, then all of a sudden all of this logic completely falls apart and doesn't work anymore. Because if you have an infinite number of points, then no longer does one have to be the largest, because each number can be bigger than the number just before it. And so you could potentially have no maximum value, or similarly no minimum value. So once we know that we're dealing with just a finite number, just these numbers on the left side of this n, we can pick out the biggest one. If we didn't have this starting point at n, we couldn't pick out the biggest one because we would have an infinite number of points. Okay, that's a little bit subtle. Hopefully it made a little bit of sense. If not, we'll have a lot of the semester to talk and think about these ideas. Okay, let's go ahead and move on to what our final activity is for this semester, or for tomorrow. I'm going to talk about convergent sequences. And I think most of you kind of know what we mean when we talk about convergent sequences. So we have some sort of graph like this, and we have some point that it's converging to. So I'm going to call it L. And then our sequence, well, we're not sure what it's doing. It could be moving around. But what we know is that our sequence eventually kind of gets really close to these L values. And that's what it means to be convergent. Now, quick warning, I'm going to ask you to create a definition. If you're using a word like gets really close to L, or is very, very near L, or is almost L, or has a limit of L, then my question I'm going to ask you is, what does gets real close mean? And what does has a limit mean? And so our goal in this class is to take these words that are vague words that we use throughout calculus and try to make them more precise. What does more precise wording look like? Well, more precise wording looks something like what we did with eventually bounded. Things that have, there exists a number such that this happens. For all numbers, there's this inequality must be true. So try to hinge your definition on these types of things that make sense mathematically, and shy away from those vague words like it always happens, or it gets really close to, or it approaches, or things like that. Okay, so with that said, here's your task. Your task is just like it was yesterday. Create graphs of as many different examples of functions converging to 0 as possible. So we're going to start by just thinking about converging to 0, because it's a little bit simpler to put the definition together in that case. So come up with as many examples and then as many non-examples. So start with examples and then go to non-examples of 0. And then finally, complete the definition of what happens if a sequence converges to 0. If we get this definition tomorrow, I'll feel like we did a really good job and we're well on our way to being successful. But it's possible that some of you have already seen some of these ideas or thought about them, or you're just really starting to connect to the things we've done. And if so, if you feel like you've made sense of this task, move on to the last possible task, and that is, what if we replace 0 with 10? It might seem like it'd be really easy to switch from 0 to 10, but there's some subtle things going on that it's easy to not make that transition automatic. So if you feel like you have 0, then try 10. So again, finish all your homework for tomorrow. Once you finish your homework, try these tasks. Make sure to come to class with some graphs drawn, and make sure to come to class with a definition, even if you know it's not right or it's not perfect. Writing something down is the first step towards making progress. Okay, so write out your definition for 0, and then if you're feeling good about it, go ahead and think about how would we expand that to the number 10. Okay, I look forward to seeing you tomorrow. If you have questions, especially about the homework, but really about anything, don't hesitate to contact me in the morning, and we'll find a time when we can sit down over Zoom and work some of these things out. So thanks so much. I will see you.